But it's my pleasure to welcome our first summer 2026 lecturer. She's here to present our first summer lecture in climate data science. This is Lily Xu. She is the Sun Wu Assistant Professor at Columbia here at the Department of Industrial Engineering and Operations Research. So her research develops AI methods across machine learning, optimization, and causal inference for planetary health challenges with a focus on biodiversity conservation. Her work provides novel algorithms to enable practitioners to make effective decisions in the face of limited data, taking actions that are robust to uncertainty, effective at scale, and future looking. And she also partners closely with NGOs and interdisciplinary researchers to bridge research and practice. And she holds a PhD in computer science from Harvard. And you were a postdoc at the University of Oxford with the, am I saying this correctly, Leverhulme Center for Nature Recovery. And today she will be presenting high stakes decisions from low quality data, AI for biodiversity decisions. Yep. So welcome, Lily. Thank you.
Thank you so much, Catherine. Hi, everyone. Welcome to Columbia. Welcome to LEAP. Very excited that you all are here, and it's such a pleasure to join you. So I'm happy to keep this kind of conversational, so interrupt me with questions. Feel free to just whatever comes to mind. So as I imagine you all are very, very well aware and probably are working on in your projects, our planet is facing many simultaneous challenges from biodiversity loss, climate change, public health challenges like maternal mortality, and food insecurity. And all of these challenges are interlinked. So planetary health is a framework that thinks about the interconnectedness of these challenges and how we can work on addressing these problems in tandem. And just as a few examples, biodiversity conservation can serve as like a frontline tool to help address the climate crisis, as nature-based solutions can contribute up to 37% of the CO2 mitigations necessary to meet the Paris Agreement and halt climate change. And simultaneously, climate change is exacerbating the biodiversity crisis, stripping species of their climatic habitat range. So I'll focus today on the biodiversity crisis. And just to put this in context, in 50 years since 1970, the WWF's Living Planet Index identified that the average population of vertebrate species around the world has declined by 73%. And there's currently 1 million species in danger of extinction within our lifetimes, out of only 8 million species on this planet. So it's a very large-scale problem. And part of the value of biodiversity is beyond the climate benefits it provides. It's also a frontline tool for improving human health. So a really nice paper from 2 years ago showed that the decline of a single keystone species, the collapse of vultures in India, caused the increase of human mortality by 4%. And notably that this was a ecosystem collapse that occurred in 1993. And it wasn't until 30 years later that we actually understood the impacts of what this meant for society. So it's really important that we kind of take preventative measures before it's too late. And it's also, biodiversity is also very important for food insecurity, or for preventing food insecurity, as the harvest of wild animals through bushmeat and fish is a main protein source for over 1 billion people. So simultaneously, we're also seeing a lot of global action coming up to help address this biodiversity crisis. So in 2022, we had the equivalent of the Paris Agreement for nature. So the Paris Agreement was in 2015. 7 years later, the 196 countries around the world signed the Global Biodiversity Framework, which agreed to many things. The most notable being the 30 by 30 initiative, which is a commitment to increasing the amount of the world's protected lands and oceans to 30% by the year 2030. So this means nearly doubling the amount of the world's protected lands and over tripling the amount of the world's protected oceans. But unfortunately, even inside the areas that we've designated as protected for biodiversity and wildlife conservation, there's still very major threats. So I'm actually sorry, I'm missing a slide here. Sorry. It's a powerful picture, so I wanna I wanna make sure that we see it. Okay. Okay. So one of the biggest challenges even within protected area is poaching, which is the legal harvest of wild animals. So this is a Guardian article of Murchison Falls National Park in Uganda, which is a park that I've had the privilege of working with for over 8 years now. And here's a team of rangers in front of this mountain of snares that was collected by the park in a single calendar year. So every single one of these little wire traps was something that was laid out by poachers to try to capture wild animals. So every small wire snare corresponds to one animal life that could have been lost. And these big metal contraptions you see at the bottom are claw traps meant to catch big game like elephants and buffalo. So ecologists have estimated that in Murchison Falls, there's over 4 snares for every square kilometer in the park. And this is a massive 5,000 square kilometer park. So that's about 20,000 snares. It has the highest snare density of anywhere in sub-Saharan Africa. But unfortunately, we have strong resource constraints, and there's only 250 rangers available to conduct patrols and find and remove these snares to protect wildlife and prevent poaching. So it's a very critical challenge of limited resources, and my research is focused on how can we help rangers plan patrols to more effectively prevent poaching. And part of what makes this problem really difficult is that snaring is super hard to detect. So first of all, these parks are really massive, but the snares are quite small. So here are 3 photos of snares that were placed in the park. And even though they're kind of head-on shots, it's really difficult to see where the wire meadows are. So here's just representing exactly where they are in these photos. But this just gives you a sense of like the difficulty of the challenge that they face on the ground, and also hints at the potential data, the poor data challenges that we're also going to be facing. So the data that we do have available comes from ranger patrols. So working with the Uganda Wildlife Authority and a conservation organization called SMART. They've collected many, many years of historical patrol records that log where they go and what they see. So here is Murchison Falls, and every single brown dot corresponds to a GPS location that was tracked, indicating where they went over the course of, here I'm visualizing 6 years. And you can see that even though they've covered much of the park in 6 years, there's a few places that I haven't visited even a single time. So that's everywhere in green. And what we're wondering is, are there potential poaching hotspots that they might be missing out on that we can use machine learning or other AI tools to help them identify so that they can allocate these limited resources more effectively? So aside from the location of where they've been, we also have some observations that might include ecological signs, like we saw elephant tracks, where we saw signs of a leopard, or indications of poaching activity, like observing a snare or ashes from a poacher's campsite. And what we can do, and I'll talk through this very quickly, is we can build machine learning models to try to predict poaching risks throughout the park. So taking this historical data, we can discretize the park into 1 square kilometer regions where every pixel corresponds with 1 kilometer in the park. And we can see how much effort that rangers spent covering the ground. So effort is measuring the distance traveled within 1 month. And then we can also measure the amount of poaching activity that was observed in each location. And we add to that a bunch of geospatial covariates that capture everything from the geography of the land, like land cover or elevation, to human features, like how far are we from the nearest road or patrol post. We also have information that comes from remote sensing that capture dynamic information over time. So that's like temperature, precipitation, and vegetation, which enable us to capture climatic changes and seasonality. And taking all this together, we can use what is now fairly standard machine learning tools to identify poaching hotspots and predict poaching risk in the future. And there are a few things that we have to do using ensembling techniques to help overcome data imbalanced class labels, because we have a lot more negative labels than we have positive labels. But I won't talk through that in detail here. But as researchers, what we were really interested in is not just how well are we performing in terms of the metrics that we're familiar with, like accuracy and AUC or recall, but we really wanted to understand how can we translate this work into recommendations on the ground. What are the kinds of decisions that they're actually making? How can we take these machine learning recommendations and make them useful to practitioners? And also, like, is our model actually making good predictions on the ground rather than just in terms of like the measures that we are evaluating? So to assess this, we implemented a series of field tests over the course of 5 months to assess the quality of our predictions. And for this, we took our model's predictions and bucketed into regions that we predicted to be high, medium, or low risk of poaching. And to keep this a valid experiment, we focused on areas that were infrequently patrolled in the past, so we weren't just relying on historical patterns. And we also kept it a blind experiment by not informing them of the risk classification in advance. So then rangers went on these patrols, shared their data back with us, and what we found is that they observed many more snares in the areas that our model predicted to be a high risk of poaching than medium or low risk, indicating that we were effectively able to discriminate between relative risk of poaching. And then in a subsequent month, when we were focused on high-risk areas, they found over 1,000 snares in a single month, which corresponds to a typical team finding between 300 and 500 snares. So this was a significant impact for them, and we were really excited to get this positive feedback from our collaborators at WWF as well, saying, I'm very excited about these results, and let's get this going on other countries as well. So for a lot of my PhD, I spent a lot of time really focused on like the translating research to practice component, working with the SMART, which is this consortium of 8 different conservation NGOs. And they are the ones who have built up this platform that's used by rangers and protected area managers on the ground to track and start like taking a data-driven approach to patrolling and wildlife conservation. But the platform that they have, which includes a mobile app that rangers use to track things, and the desktop version of the software that's used by managers, was only a database, so had the ability to like visualize and query, but had no ability to predict or prescribe recommendations. So what we built was a plugin that kind of attached within the system so that park managers could generate predictions on their own without having to go through us as an external party. And this was meeting them where they already are on the platforms they're already using, so they don't have to collect new data or get familiar with other technologies. And the SMART platform is widely used in many parks around the world, but not all of them have the kind of data availability that Murchison Falls does. So they have many years of patrols and fairly good coverage. But there's other parks on the SMART platform that are just beginning to conduct patrols. So Royal Balloon State Park in Malaysia, for example, only had 3 months of observations. Like much of the park had not been explored at all. And they reached out to us with really a lot of interest in getting more informed patrol recommendations. And we said we'd be happy to work with them. But when we saw this as their data, we said this is simply not enough to bring into a machine learning model. But what this told us is what we should be focused on next from a research perspective of not only building models for data-rich parks, like the ones in Uganda, but also focusing on data scarce parks, where we have to think about how can we not only identify like hotspots we've already identified, but also do exploration in areas that we have a lot of uncertainty so that we can improve our model in the future. So this is really kind of like balancing the short-term gains from going to areas that we already know to have a high risk. So we can call that exploiting data areas with a lot of certainty, and then taking more proactive patrols to improve our predictive model requires exploring areas with a lot of uncertainty. So balancing this trade-off between exploration and exploitation is a key challenge in these data scarce settings. And a common approach to addressing these kinds of challenges is known as online learning within the machine learning umbrella. Yes?
Like, can you explain exploitation part? Because I've seen like you explain it lots of like, but I usually understand exploitation.
Yeah. Yeah, so exploitation here is not meant to have a negative connotation. It's just the terminology people use, but I recognize that it does have that negative connotation. But here we're just kind of like going with the familiar route. You know, we're taking we're trusting, like maybe if they like found a lot of snares here, we're not going to neglect it. We're going to make sure to send some people there. But the challenge is if we only always send people to the highest place that we've seen in historical data, there's so much that we've missed. Or even in other places that we've explored, like maybe we just like happened to go there on like a really rainy day. So there wasn't poaching activity, but then if we came back like in the summer months, for example, there might be actually really high poaching. So what we have to do is recognize that exploitation is just blindly trusting the data that we've observed so far. But exploration means that we also have to think about how to quantify the uncertainty in the areas that we haven't explored yet or that we've underexplored, and make sure to balance these two.
So you can typically rely on exploitation much more, like when you have like those parks as you mentioned that have a lot of data.
Exactly. Yeah. And the key challenge here is like if we have no data, we want to or if we have like minimal amount of data, we want to almost completely explore. But then as we collect more and more data, we want to exploit more and more. But figuring out how to like do this in a statistically optimal way is where online machine learning helps to give us like a very principled framework for doing this. So the approach within online learning that is commonly used is called a multi-arm bandit, where every arm corresponds with like an action that we could take. And to just talk about this at a very high level, what our work is focused on is how can we help online learning algorithms do work operate more efficiently, because they're typically evaluated in terms of their like long run asymptotic performance over an infinite time horizon. But what we have in our context, because it's a very high stake setting, is we actually want to reduce, we want to minimize any like poor performance in the very, very early round. So we don't want to do unnecessary exploration. Because we can't say, okay, we're just going to have you do a lot of exploration for 1 year. And then after that, we'll start to do more exploitation, because by then all the wildlife will be gone. So we really have to make sure that we're only exploring as necessary. And what we can do is by leveraging problem structure that comes from understanding of the domain, we can figure out how to translate that into like mathematical principles that we can bring in to this online learning multi-arm bandit algorithm to help reduce the amount of unnecessary exploration. So just to summarize that again, exploration is expensive. It takes resources, it takes time, and comes with steep opportunity costs, because the alternative is that we could do some exploitation. So by integrating ecological insight and domain knowledge as priors, this can help constrain and guide our machine learning model to do better with not only the data that we have, but also like the human knowledge and expertise that is available. Yeah.
So with the whole idea of exploration being expensive and kind of difficult to do, when small parks are reaching out to you that might not have much time when you were still getting established, how often are they willing to go down the exploration route that might be a little difficult at first, but yield better results long term versus just leave it altogether?
Yeah, that's such a great question. I'm really glad you asked that, because actually, like when we were first working on this problem, when we were first talking with Royal Baleen State Park in Malaysia, we recognized, okay, you don't have very much data, and there's an approach with the machine learning called active learning, which is where we find the areas of the model that have the highest amount of uncertainty, and then we collect data from those points and use that to improve our model. So it's really, active learning is fully focused on improving the predictive model. So we kind of worked through this, we built some initial models, and we came back to them and pitched this idea of, okay, for a month, we're going to do information gathering patrols and just like go to areas without uncertainty and focus on collecting information so that our model can be better. But the reaction was, unfortunately, we can't spend an entire month only on information gathering because we'll have the challenges that you're alluding to, where that means we're just going to be compromising areas where we already know is valuable, and that told us, okay, well, we therefore can't take an purely active learning approach. We also have to do we can't only explore, we also have to do some exploitation as much as possible, and that's what made us pivot to applying online learning as a framework instead. So kind of like working through and like iterating the problem construction with our with our partners really guided the process of like what approach to even take, recognizing like what was feasible or not feasible in their mind.
Are you going to talk more about the online learning part? Because if not, I don't know what that is.
Yeah. I wasn't. Yeah, I have another version of this, but I want to do this at a little bit more high level. So yeah, we won't go into too much detail about that. I'm sorry. Okay, but to kind of give a teaser of the types of like domain insight that we can bring in. So one is decomposability. And this is recognizing that the action that we have to take is not just which single region to explore, but we have to make these decisions in kind of like a batched context. So we really have to make a decision for the entire week or month. And that tells us not just like, okay, go to this area, but go to these subsets of areas. So this puts us in a combinatorial action space where we're kind of selecting out of n regions, we have to select some k subset. So it's like a k choose b size problem. And importantly, because we have imperfect observation, where, as we saw, snares are very hard to detect. So the challenge is if we go on patrol somewhere and we don't find a snare, we don't know for certain that there's no poaching activity. It could be the case that it was just like very, very well hid. And maybe if we like searched a little bit longer or we like went back the following week, then we would observe it. So the key insight that we have there is we can use the amount of patrol effort as a proxy for how reliable our negative labels are. And what that's just telling us is basically, if we patrol really intensely and we don't find anything, we can be much more confident that there is indeed no poaching than if we only patrol for 30 minutes or half a kilometer or something like that. So from a like action decision standpoint, this means that we have to consider not just where to go, but how much time to spend in each region. Because maybe some areas will have diminishing returns that are steeper than others. So the core like construction of our problem has this combinatorial structure, and then we want to break it up and leverage the fact that there's decomposability in this problem structure to make it to take us from this like very large exponentially sized combinatorial action space to a more linear one that we can tractably search over. And then the other component that we leverage is smoothness in our reward function. And this tells us two things. This tells us that if we have a good understanding of how much patrol, how likely we are to find snares if we patrol a certain amount at, let's say if we patrol for like 4 kilometers, that gives us some understanding of how likely we would be to find snares at 3 levels of patrol, 3 kilometers of patrol effort as well. So there's kind of like smoothness in our expected reward or utility or probability of finding a snare in that space. But there's also similarity across the different geographic regions as well. So we can take the landscape features, and if two areas are very, very similar and they differ only in terms of like 100 meters of elevation, then we also expect that their poaching behaviors will be similar as well. So we can leverage smoothness across the feature space as well. And then what Lipschitz continuity tells us is that it's just like a mathematical definition of smoothness, where it tells us that the function won't change by all that much. And it just says that there is some maximum derivative across the entire function space. So we're never going to have like a derivative that like suddenly changes like really, really sharply. But rather, if we have the maximum derivative is like 1, then we know that the entire reward function will not deviate too dramatically. And that enables us to take understanding that we've already seen in one area and translate it to other components too. And the last aspect that we have is recognizing that if we have a good estimate of how likely we are to find snares at 3 kilometers of patrol effort, that gives us an upper bound over how likely we are to find snares at any lower level of patrol effort. So the fact that there's monotonicity in our expected probability of finding a snare as we exert more or less effort are all things that we can bring in as mathematical constraints to reduce the amount of uncertainty that we have, and therefore explore less, and therefore obtain higher reward within even the short time horizons that we're considering. And what I want to emphasize is that by like identifying problems that really come from these real world challenges, this translates back into like new research ideas, new algorithmic and mathematical insights, because not only were we able to bring these together into a new algorithm, we were also able to contribute like new mathematical results that adds to the theoretical basis of online learning by combining combinatorial bandits with Lipschitz bandits. So really kind of bring things together by addressing a new model that emerged from this problem setting. So I think that is just, really trying to encourage you all to continue working on these kind of like real world applied problem settings, because even if you're also excited about like foundational fundamental research, it is a really good way of kind of identifying those types of problems. Okay, so another question that you might naturally ask about this setting is, how do poachers respond to our patrols? Because everything that we've been modeling so far assumes that, yes, things might change between like January and June. So there might be seasonal changes because those are things that we can measure. We're assuming that, as long as like this region has like the same like temperature and seasonality and everything like that, it's going to have the same patterns as whatever previous poaching patterns we observed. So that's an assumption of stochasticity, that there will be noise in what we are observing, but the expected probability of poaching will always stay the same. But if we really think about this setting, we might recognize that poachers are strategic humans, and they don't want to get caught. And they also want to make sure that their snares aren't confiscated. So if they realize that a lot of their snares are being taken away by rangers, they might move to somewhere else and respond to what we're doing. So what we're really interested in is trying to understand what does the response look like, and then more importantly, how can we plan around that? So by looking at data from both Queen Elizabeth and Murchison Falls National Parks in Uganda, what we found is that when rangers patrolled more in 1 month, the likelihood of poaching in the subsequent month went down. So there is deterrence. Ranger patrols actually are making a difference. And we also saw displacement. So the areas around the areas that we patrolled more had a little bit increased poaching. So there's this kind of, cat and mouse effect that's occurring. But what this indicates to us now from a research perspective is that we need to think about the sequential nature of this problem setting, because we are now working in a dynamic environment where poacher behavior is changing over time, and we want to anticipate and ideally respond to this as much as possible. So if we are to make some estimate, like we estimate this the strength of deterrence to be a 17% reduction if we patrol a certain amount. The challenge with our setting is that because our data is imperfect, we can't be too confident in whatever estimate we make. There's going to be uncertainty, and we might be better off saying that we think that the reduction in poaching will be 17 plus or minus 5%. But now uncertainty means that we have to think about sequential planning in a dynamic environment that also has uncertainty. So to address sequential planning problems, a common approach is known as reinforcement learning in machine learning. But then the fact that we have to address uncertainty in our model of the world requires robust planning. So now we want to think about robust reinforcement learning. And a common approach for robust planning in sequential problems is what's called maximizing the minimum reward. So that's like a common objective that has been historically used. And I'm gonna describe what that is and also argue for an alternative objective. So for this example, we're going to look at this, take some environment parameter, let's call it Z, and say Z can take on one of three values. It can either be 12%, 17%, or 23%. And here I'm making it discrete for the sake of explanation, but it could work for continuous problems too. So now we have three possible settings for the world, and we can evaluate if Z were 12, what is the best actions that we could take? And then how much reward do we expect to get for that? And similarly, we can do the same thing in isolation for 17% and 23% and assess what is the best like sequence of actions to take in each of these settings. What should we be patrolling? How should we be changing over time? And how good do we expect to do in each setting? And we can also look at, for each individual setting, the worst performance. So this gives us an upper bound and a lower bound. And what that means is if we have an upper bound and a lower bound, that means we have an understanding of like what the space of our decision quality is. So for any possible sequence of actions that we take, if we're assuming Z is either 0.23 or 0.17 or 0.12, then we know the range of possible reward that we can get. Like we can understand how good we expect our performance to be. So now let's assess the potential robust objectives that we can consider. So if we now look at one policy, which is a sequence of actions, so we're considering like, okay, what if we apply this this action to all three settings? How well will this policy or sequence of actions perform if it's 0.12, it performs as well. If it's 0.17, it performs as well. If it's 0.23, it performs as well. So we see that the reward will differ in each setting. And what the commonly used objective of maximizing the minimum reward is, we'll recognize, okay, our policy does worse when the setting is 0.12. So if we want to maximize the minimum reward, we want to change our policy so they can do better in this setting. But what you might recognize is that our ceiling is really low. So even though our reward is the lowest in this first setting, there's only so much better that we can do. Like the marginal benefit of improving in the setting is very, very minimal. So instead, a metric that is really useful to consider here is known as regret, which is evaluating not just how good I'm doing, but how good I'm doing compared to like what my potential is in this setting, because this is just a very, very hard setting. And here we see that the regret is actually lowest in this context and much higher here, even though the reward in this third setting is higher. So the setting with the maximum regret is this third setting. And instead, another objective could be to minimize the maximum regret. So we would adjust our policy to try to do better here, so that we could potentially have like a huge jump in reward here. And even if that might make our performance here a little bit lower, that's okay, because like the change is going to be very minimal, whereas the potential change in this other setting will be much, much higher. So the kind of commonly used objective of maximizing the minimum reward, we argue, is overly conservative and focuses too much effort on this worst case scenario, even if like the potential is not very high. Whereas this other objective of minimizing maximum regret, I think is a little bit more like holistic by focusing on improving our decision quality rather than just being too conservative. So just to talk through this very quickly. So now the objective that we have is we want to find some policy that I denote as pi. So this is a set of actions. We want to find some policy that will minimize our maximum possible regret over any potential value of Z. And regret is defined as how good we do, so how good our policy does if Z is either 0.12, 0.17, or 0.23, compared to an optimal policy pi star. And this objective is very difficult for a few reasons. So one, this policy pi is sequential. It's not just what actions we take today, but what actions we take today and then tomorrow and then the day after that. And as we mentioned, it could also be continuous and multidimensional. So there could be many things we have to decide. And Z can also be continuous and high dimensional as well. So we have to find some pi out of this like very large space that minimizes our maximum regret where over this large space as well. So this becomes a very computationally difficult optimization problem. And furthermore, this new objective of regret of not just maximizing the minimum reward, but minimizing the maximum regret makes this problem even more difficult, because regret is how good we do compared to an optimal policy for a current z, which means that every time we change z just a little bit, then the optimal policy for whatever new z is will also change. So we're kind of like chasing a moving benchmark, and that means there's an underlying maximization problem here too. So it's really, we have to find a policy that minimizes our maximum regret over all possible environment values, and then we have to solve for whatever the optimal policy is as well. No, this is a very hard problem, and to just give a very quick teaser for how we can overcome it, we can apply ideas from game theory in order to solve this min-max problem more efficiently. So instead of having to identify all the potential policies pi and all the possible environment settings z, which are just too big to enumerate, what we want to do is we want to search these spaces in a very efficient way by finding, okay, what's one good policy pi and what's one good parameter environment settings for z, and then slowly adjust those over time to make sure that we're exploring the space well. And we use this approach known as double oracle that just sets us up as a two-player zero-sum game, where we first start off with just a single policy for both the planner that's trying to find an optimal policy pi, and what we call nature that's trying to be adversarial and find a worst case environment setting that will make our regret as high as possible. So we just start off with like one pi and one z, and then we say, okay, well, if it were z, how good is my pi doing? And then what's a better pi? And then for this like new pi, what's a better z? And then by slowly building up the space, we're able to identify an optimal policy within a finite number of time steps. So this is just taking ideas from economics and AI and mathematics to help us solve these difficult problems. Okay. There's another thing I had here, but I want to jump to this bit. Okay, so for a slightly different approach in my work, I also wanted to talk about related to conservation is some of my work on invasive species management. So to put this in context, invasives are a huge problem for biodiversity conservation, and so the invasives play a key role in 60% of all extinctions worldwide, and this is particularly acute on islands. So 90% of extinctions on islands are driven by invasive species, and especially from a perspective of like environmental justice, this is very acute, considering that island communities are some of like the most poor and vulnerable. And the invasives cost the global economy more than $423 billion annually, according to an estimate by the World Economic Forum. I can't even wrap my head around what that number means, but it's a lot. So I'm specifically focused on a problem of invasive species management in the Florida Everglades. And to put this, actually, how many of you have heard of invasive Burmese python in Florida? Okay, Dan is familiar. Okay, so it's a huge, yeah.
About the python hunt.
Oh, really?
Lower Manhattan Plain.
Right now?
Right now. They put out a reward for people who go into the Everglades and hunt python. There's a documentary currently playing.
Oh my gosh.
In the Lower Manhattan.
Do you know what the documentary is called?
I can look it up.
Okay.
If you guys want to organize the outing.
Oh, cool. Oh, super cool.
Lily will go with you.
I would. And I'll bring my PhD student too. Okay, so Burmese python are a huge challenge in the greater Florida Everglades. So there's an estimated 300,000 of these invasive snakes, and they prey on 90% of native wildlife, and they get really, really big, so they even eat alligators. And over the course of its lifetime, each python consumes 460 native animals. So just like think about the amount of destruction that 300,000 of these snakes can do. So for invasive management, as Tana alluded to, the state of Florida has this program called Patrick, which is the Python Action Team Removing Invasive Constrictors. And basically what they do is they pay residents as they employ them as contractors and pay them for finding and removing these snakes. So they get a certain amount of money for every hour that they spent, every snake that they find, and they get more money for snakes of a certain size. They get more money if a snake is a gravid female, it means that she's carrying eggs. They get money for like egg removals and nest removals. And this Patrick program has been run by the startup called Inversa, which is focused on invasive species management. And they're doing something that I find very, very clever, which is finding ways to like fund this large scale work, because the state of Florida is investing $2 million in this, but it's such a large scale problem that we really need to bring in more money, ideally from private finance sources as well. So Inversa is trying to connect this work of ecological restoration with the private marketplaces by finding a way to like take this removed biomass and sell it on the public market. So any ideas for what approaches they might use? Like how can you make money by removing snakes? Yeah?
I'm thinking like first.
Yeah. Okay, so Inversa is focused on connecting this like invasive removal with the high-end fashion market. So imagine buying like a snakeskin purse or boot that is actually regenerative for the environment. And this is also really wonderful because that means there's like a large marketplace for this, and people are willing to spend high premiums. And to just if anyone's scared of snakes, maybe close your eyes for the next 2 seconds. But to see just some of the folks who are kind of doing this on the ground. This is Carl Jackson, who in February caught this snake. So this is a 16-foot Burmese python that he caught with his own hands. And weighing at 202 pounds, this is the largest python ever recorded in Florida. So this is just how big they got. This is running around Florida this year, which is absolutely wild. So for the Patrick program, they have 50 contractors like Carl who are doing this. It's a $2 million investment by the state of Florida. So what we're really interested in here is helping them say, okay, even though there's like this money brought in, they have these contractors, it's still, again, a very like limited population of people who are able to do this restoration work. So in order to model this problem, we have to think about like all the different players involved. So on one side, we have the Florida Fish and Wildlife Conservation Commission, FWC. And on the other side, we have like the individual like hunters. So FWC wants to improve catch per unit effort. So they're paying people every hour. They have like a limited pool of contractors that they can employ at any time. So for every like hour that people are spending out in the field, they want to help improve the number of snakes that they can catch. And we, similarly to the last problem, they collect very extensive like GPS data about where they go and where they're finding snakes. So we can keep track of all this like historical information about snake observations. And we want to learn patterns across the landscape. So again, we want to like learn like similarities based on ecosystem characteristics and climatic information. So here, things like humidity and temperature really, really matter because snakes are more active in the rainy season during the summer than they are in the winter, they're more dormant. Yeah.
So maybe a silly question. Don't the snakes fight back? How do the guys?
They do. Yeah, they wrestle. Yeah.
So how can you just did he like make him summon or something? Or?
They like this is like a live snake, but there's like videos of it. Because if anyone's on TikTok, there's like this like guy called the Yoink guy. I haven't seen it. People keep telling me that there's like this guy, the Yoink dude, on TikTok. He just like picks up like snakes, he yoinks them out. So yeah, they are like very highly trained contractors. Like many of them like were like are veterans. They've just like loved being out in the bush. So I would not meet the standards for this. Yeah, but this is also kind of like the difficulty of this task is also helping us recognize like the magnitude of the challenge of being efficient with our resources. Okay, so we want to like figure out like what are like general patterns of like snake behavior, and how can we help make better recommendations to these hunters about where they should go. And similarly to what we just saw, there's still a lot of uncertainty. So some areas are very remote. Things are changing across seasons. So again, we have to do some exploration and exploitation balancing. And from the perspective of the hunters or contractors in the setting, even though we collect this like very rich data about like where they go and what they find, there's privacy concerns that prevent us from sharing this data with each other. So we can't just say, okay, here's everyone's information, like make of this what you will. Instead, we are able to observe it, but we are not the ones actually going on the ground. So that's the trade-off we have to balance. And then unlike the rangers, where if one person is successful, then everyone is successful. Like it doesn't matter if my team finds snares versus your team finds snares, but for them, they get individual payments. So they want to be the one catching snakes. It doesn't help if like, somebody else in the program is catching snakes. So you don't want to have like one person exploring and the other person exploiting. You want to make sure that it's kind of like fairly balanced. So these are the considerations that we have to address. So just to quickly talk through how we can like set this up as a model. So we can, what we assume is that the objectives of both the state agency, FWC, and the hunters are the same. So this is just how the program is set up. The contractor pay is proportional to the value for the state agency of if you find a snake or a nest or eggs. And then we have all of the historical observations of like where they go and like whether or not they're finding snakes. But each contractor only has a subset of these observations. And that means FWC, by having global observation of everything, can find the action that best balances exploration and exploitation. And we can employ similar approaches for multi-armed bandits here. But even though we identify the best action to take, each contractor will identify their own best action J that they think is optimal based on their subset of those observations. And this really does happen. Like the contractors have areas that they like know to be kind of like snake hotspots. So they're often just like going to the same place, especially because it's a very large region in Southern Florida. So they kind of go from their homes, they have like areas that they're more familiar with. So all of them kind of like have their like little clusters of like, okay, this is where I go. And they will do a little bit of deviation, but for the most part, they kind of like stick to what's familiar. And what we want to understand is because we have like designed this like whole like payments-based program, can we pay them a little bit extra so that they take the action we want them to take instead of going to the areas that they will naturally go to on their own? So it's just kind of like, instead of only paying them $200 per snake, because the thing is, they don't want to go to the area that we're recommending because for them, there's uncertainty. Like they would rather get 200 guaranteed dollars or highly guaranteed dollars than go to an area where they, might only get the $20 hourly rate. So we want to understand, okay, well, we can pay them some additional value, but we don't want to overpay them because we still have like a limited budget. So how much and what can we pay them so that they will actually take the action that we want them to take? And in order to be incentive compatible for them to actually accept our recommendations, the bonus that we have to pay them needs to be the difference in what they estimate like the value to be for the areas that they prefer versus what we prefer. So that's something that we can kind of estimate based on the historical preferences. And there is some literature applying online machine learning using multi-armed bandits to this kind of like incentive-based problems. But those problems assume that all of the agents are completely myopic, so that they're only thinking about like, okay, what is the best thing for me to do now? Should I accept this payment or no? And then disappear forever. And while that assumption might be reasonable in some kind of like digital settings or like online marketplaces where we have a lot of like different players. So for example, Google Maps wants us to do like a little bit of exploration, because they want to understand like, okay, what are traffic patterns like in that street? They don't want to just like give everyone the same information. But like me as an individual, I never want to like, drive a longer route because that helps Google collect data. Like that's not beneficial to me at all. And from Google's perspective, like they have like millions and millions of users. So they don't have to work, even though that I might like log onto Google Maps every day or every week, they don't really they can kind of like assume that I just like appear once and then disappear forever because like across millions of users, like me coming back 10 times doesn't really make a difference. But for us, we have a very small number of agents. We only have 50, and they would come back, multiple times a week. So the fact that they're repeatedly returning really does matter for our context. So the key difference in our problem setting versus the existing work is that with returning contractors, these agents are no longer purely myopic. That they, as we mentioned, do a little bit of exploration on their own. They'll figure out, okay, maybe today I'll try something new, and they might identify like, okay, here's like a really promising area that I was missing before, so I'm going to spend more time there. So they might naturally self-align to whatever FWC prefers. And what this tells us is that it might be cost effective to strategically wait a week instead of offering a bonus every single time. Because if we offer them a bonus, they might always require that same amount of bonus to do the action that we prefer. But if instead, we let them just kind of like go to the area that they think is best, and maybe they got lucky in the past, and then if they keep going, they won't get lucky anymore. And they realize, okay, this area is not so good, let me go somewhere else. So these are the kind of considerations that we want to balance. But like we don't want to always wait because that means we're not leveraging the like global information that we as FWC have. So the algorithm that we propose gives us like computes exactly when we should wait and when we should bonus based on our estimates of how many observations it will take of the contractor to either go to the areas that they think is best versus go to the areas that we recommend for their preferences to be aligned with whatever our preferences are. So this is like the approach that we have, and this is still ongoing work, so we're in the process of like analyzing this algorithm more mathematically, and then ideally deploying a pilot with them. So that is all work in progress. So I'll wrap it up there and just mention that my research group here is called the CAP Lab. We develop computation algorithms for people and the planet, and I'm around. So thank you all for your time, and it's very much a pleasure to be here.
It's like AI.
Oh, okay. Yep.
So,
Will you tell me your name and where you're coming from?
Gabriel.
Okay.
Yeah,
Right.
Gabriel.
Gabriel.
Wonderful presentation, very interesting topic. And my question is more about the machine learning setting you use to predict the risk. So my question is, did you use did you look at the spatial correlations and like a spatial and temporal contiguity? Because I think that when a trap is placed placed in a spot, like in a geographical location, it's more likely that another one might be placed in a location close by.
Yeah.
Right, and that's true also in a temporal perspective, because maybe these are areas that people know.
Yeah.
And they are more likely to place the trap
Yeah.
in over there. And this is like one question.
Yeah.
And again, also, okay, the second one is about the confounders. So, I mean, when you use these environmental predictors, and you observe a certain risk predicted by the model, did you explore if the risk makes sense according to the input predictors in that specific location and at the specific point in time? Or that risk can be, for example, explained by other variables that you didn't observe and didn't account in the model?
Yeah, great questions. So for the first one, oh my gosh, I'm forgetting it. Oh, so what we did in the predictive model. So what I described here, we weren't accounting for that kind of spatial correlation. We actually have a paper that came out earlier this year that is improving upon our predictive models of poaching risk. And our original work was using Gaussian processes and random forests, which back in 2018 when we were working on this were more kind of state of the art. Now we applied diffusion models to this. So using models used for generative AI and for image generation, because what diffusion models are able to do is they capture exactly what you mentioned of like spatial correlations between different areas. And this will enable us to say that like if we have an estimate for kind of like one pixel, then like nearby pixel, that gives us some information for like what nearby pixels should look like. So we are able to account for that a little bit more directly with a diffusion model based predictor. And then for your second question of potential like unmeasured confounders, they absolutely are there. There's so many things that are like very, very difficult to measure. So other things, it's like environmental factors that we can't measure. So if we're interested in like, okay, where are jaguars within the landscape? We would like to know like where the prey are, but that information is like not available to us. So if we're interested in like jaguar poaching, we would really love to have information about like prey availability and density, but that just simply information that is unavailable. So you have to kind of make do without it or use enough other environmental covariates about vegetation that might give us a bit of information about like food and habitat, and that might help us identify, okay, here are areas that correlated with where jaguar prey might be and therefore where jaguar might be. But we aren't able to address those directly. So we know that there's so many of them that we haven't identified, and we're just gonna just say, take as much data as available, like kind of dump it in there. And this is also a little bit of back and forth with the parks, because they helped us identify like, okay, here are other layers that we think are going to be really relevant. Like we think that like the amount of like groundwater is going to be very relevant, or we think that like use like this measure of like vegetation index and not this other measure. There's like other measures of like habitat suitability or like cloud cover, which like as somebody who's like not an ecologist or biologist, it's hard for me to understand what's actually relevant. But for them, they have much stronger like intuition about.
Yeah, but I do think that using like a generative setting and you can provide like uncertainty.
Yeah.
Somehow you cope with the uncertainty of the predicted risk.
Yeah.
Sense and maybe you can trust more.
Yeah.
Up to certain confidence. Okay.
Yes.
So very cool. Thank you.
Yeah. Awesome. Anything else? Yeah.
Yeah, it's a great.
Thank you.
Great. Yeah. So my question is about the quality of the data.
Yeah.
So you mentioned that the major passwords are like collected.
Yeah.
So how do you make sure that the quality is to your perspective, and how much data do you have like for the training?
Yeah.
So I'm curious to see like what kind of like procedures you do before you start to do the training.
Yeah, so the data is not to our standards, but what we have to do is we have to like adapt as much as possible and just make do with what is available. So I'll give you one example of this. In the data, like not only do we get like some observation of like, okay, we found snares here, we found like elephant tracks here. There's also like a kind of like a free text box that they add to like give more descriptions. So for example, for when they find a snare, there's also an option to say, how many snares did you find? And sometimes it's like, many times it's 1, sometimes it's 2, sometimes it's 8. At one point we saw 300 and we're like, oh my gosh, you found 300 snares in like one location. And we asked them about it and say, oh no, that's 300 feet of electric wire. And we're like, okay, so even though there is like like places to have this available, it's so inconsistent, and there's like everything is an edge case. So for that reason, even though we would really like to understand like how many snares are in different areas, that information is so unreliable. We have to just make it binary. So like, is there a snare or not? So these are kind of like all modeling decisions that we have to make based on like the poor quality data, based on like the realities of like working in these more practical settings.
One thing maybe about the one your attention about the other thing observability. What's the justification for this part? Like you mentioned at some point that there is 17% uncertainty or plus or minus.
Yeah. That was just an example. I just made up that number. Yeah, but you know, you can do something like you estimate a 95% confidence interval. So especially to estimate something like the impact of patrols on future poaching, we would apply techniques from like causal inference or econometrics, often logistic regression, to try to estimate some value like that. And those approaches enable us to get confidence intervals. So we can say like with 95% probability, it'll be like within this range. Yeah.
Thank you for the presentation.
Yeah.
So I guess I'm interested in how you guys separated like the actual presence of poaching versus like you mentioned, like just because they don't say that they saw them.
Yeah.
So I guess given that the predictions are being made, you said on like a 1 by 1 kilometer, right? Is there like, I'm curious how sensitive the model is to the resolution of that effort.
Yeah.
And like for the environmental covariance, because they're at that resolution, is there like a potential for them to mask the local like ground truth reality of the snares?
Yeah, that's such a great question. And actually, I think that dovetails nicely from the last question, because even though 1 square kilometer is very large, it's very granular, we found that if we made it smaller, our data quality just like was so poor, because even though we have like many years of historical data, it's still sparse relative to the entire park. So the more like fine-grained resolution we have, then the more negative labels we have, because like if like they patrol this entire region, if they found a snare there, then this whole region is a positive label. But if we break this up into 10 smaller regions, only one of those out of 100 is going to be a positive label. So like the more granular we make it, like the stronger the class imbalance. So we found kind of like 1 kilometer to be this like good middle ground. And that is something that like that's a parameter that should vary across parks. So for smaller parks, where they have like more density of coverage, then we could use something, 100 meters, for example. But then for like a larger park, on other sites we were doing 2 by 2 predictions or 5 by 5. Yeah, so that is something that that definitely depends. And I think our ability to make estimates according to like the environmental covariance, it does hinge strongly on those kinds of modeling assumptions. Okay. I don't know if we're supposed to be moving to lunch now. Hi. Look.
Keep going with the Q&A, but we
Okay.
won't roll
Yeah,
with
yeah.
lunch.
Okay. Yeah, maybe let's move. Thank you all so much online. Great to be here.
Thank you.
Thank you. Thank you all in person.